Hello everyone, welcome back to another physics video. I'm Physics Michael, and in today's lesson, we're going to explore polarization of waves. We will cover what a polarized wave is, how light can be polarized using Polaroids, and learn about Marlow's law. Let's get started. Let's start with understanding what a polarized wave is. A polarized wave is a transverse wave that only vibrates in one plane. We call this spatial behavior polarization. Let me demonstrate with a simple example. When we vibrate a knob up and down, the wave vibrates only in the vertical plane, and when we vibrate side to side, the wave vibrates only in the horizontal plane. In fact, you can vibrate the knob in any directions that are perpendicular to the knob to produce a transverse wave traveling along the knob. However, if we put a vertical slit in the wave's path, it will constrain the direction of the vibration to just the vertical plane. This is exactly what polarization does. It restricts waves' oscillation to a single plane. Now, since that is a transverse wave, it can be polarized using a special filter called a Polaroid. In the picture below, the vibration of light wave is constrained to the vertical plane by the Polaroid. This means the Polaroid has a transmission axis in the vertical. Once the unpolarized light passes through the Polaroid, it is polarized in the vertical plane. And when we use a second Polaroid, something interesting happens. If the transmission axis of the second Polaroid, which we'll call the analyzer, is parallel to the transmission axis of the first Polaroid, light passes through completely. But if we rotate the analyzer so its transmission axis is perpendicular to the first Polaroid, no light gets through at all. This demonstrates that light waves are indeed being restricted to vibrate in just one plane. Then let's look at how polarization affects our everyday life. When light reflects from water or glass surfaces, something interesting happens. It becomes partially polarized in a plane parallel to that surface. This is why polarized sunglasses are so effective at reducing glare from water. Look at these two pictures below. The left one shows water surface in daylight without sunglasses, and the right one shows a view with sunglasses. They are pretty different, right? This is because the reflected light from water is horizontally polarized, but the sunglasses have their transmission axis oriented vertically. So the sunglasses block most of the reflected glare, making it easier for us to see. Here's another everyday example, your computer screen. Did you know that light from a computer screen is plane polarized? You can actually test this yourself. If you look at your screen through a Polaroid and rotate it, you will see that light intensity changes as you turn the Polaroid. This happens because the screen's polarized light is either being transmitted or blocked, depending on the Polaroid's orientation. Now let's talk about the intensity transmission equation through the Polaroid. From the picture below, we can see that the amplitude vector of oscillation is partially transmitted through the Polaroid's transmission axis, depending on the angle between them. And for the amplitude vector, we have transmission amplitude equals initial amplitude times cosine theta, or in symbols, A equals A0 times cosine theta. Since intensity is proportional to amplitude squared, or I is proportional to A squared, so the relationship of intensity is that the transmitted intensity is equal to the initial intensity times square of cosine theta, which we call Marlow's law, or we can write it in equation I equals I0 times square of cosine theta. Let's solve an example together. Imagine we have plane polarized light with an intensity of 12 watts per square meter hitting a Polaroid. The angle between the plane of polarization of the incident light and the transmission axis of the Polaroid is 30 degrees. What is the intensity transmitted? Using Marlow's law, I equals I0 times square of cosine theta. Plugging in our values, 12 times square of cosine 30 degrees, which equals 12 times square of root square 3 over 2, giving us 9.0 watts per square meter as our final answer. Now let's summarize what we've learned today. Polarization is a phenomenon where a wave vibrates only in one plane. Remember, only transverse waves can be polarized. Light can be polarized in two main ways, using a Polaroid filter, or by reflection from a surface. And as we saw, even your computer screen produces polarized light. Finally, we learned Marlow's law, I equals I0 times square of cosine theta, which helps us calculate the intensity of polarized light. That's all for today's video. Thanks for watching. I hope you now have a better understanding of wave polarization and how it affects our daily lives. I'm Physics Michael, and I will see you in the next video.